Picture the machinery behind a modern recommendation feed. When you open an app and content appears in milliseconds, what's happening under the hood is actually a small zoo of specialized services talking to each other. There's a model that turns you into a vector, a separate nearest neighbor search service that finds candidate items close to that vector, a filtering service that throws out items you can't see for language or eligibility reasons, and a ranking model that does the final sorting. These pieces typically live on different machines, written in different languages, with their own versioning, batching, and scheduling logic. This paper from Meta argues that this whole arrangement is holding the field back and proposes collapsing it into a single PyTorch model that runs entirely on GPUs. They call the system SilverTorch. To understand why this matters, you have to appreciate the awkwardness of the current setup. Retrieval at scale is almost always framed as approximate nearest neighbor search, or ANN search, where you find the items whose embeddings have the highest dot product with the user embedding. Libraries like Faiss and vector databases like Milvus handle this, and they have GPU implementations, but those implementations cap out at relatively small top K values, often 1,000 or 2,000 items. Meanwhile, the filtering step, which enforces hard constraints like this user only speaks English, is traditionally done with inverted indexes, the same data structure search engines use, and these run on CPUs. So a single retrieval request fans out across services, gets reassembled on the client, and pays a tax in network hops, redundant batching logic, and version skew between the user tower and the item index. Meta even mentions that in 2022, a version mismatch between user and item embeddings caused a 30% drop in production metrics. That's the kind of bug that haunts you. The core idea of SilverTorch is to treat the ANN index and the filtering index not as external services, but as tensors that are parameters of the model itself. The whole retrieval flow becomes a forward pass. You compute the user embedding with the user tower, you run a filtering layer that produces a bit mask, you run an ANN search layer that scores candidate items, you run an optional scoring layer called the OverArch that re-ranks with a richer neural network, and you aggregate multitask scores through something called a value model. All of this is PyTorch code, compiled to a graph, served by a lean C++ runtime on GPUs. The most novel piece is what they call the Bloom index for feature filtering. Here's the intuition. A Bloom filter is a compact bit array where you hash each element you want to remember into a few bit positions and flip them on. To check membership, you hash your query and see if all the corresponding bits are on. The trick SilverTorch uses is to give every item its own small Bloom filter, say 1,000 bits, encoding all of its categorical features. The query also gets converted into a Bloom filter. An item matches the query if, for every bit that's on in the query, the corresponding bit is also on in the item's filter. Now here's the clever part. They lay out the data so that instead of each thread processing one item at a time, they transpose the matrix, so each row corresponds to a bit position across 64 items packed into a single 64-bit integer. A single bitwise AND instruction on the GPU now evaluates that bit's contribution to 64 items simultaneously. This is dramatically more GPU-friendly than an inverted index, which is fundamentally a sequential list-walking data structure and a terrible fit for the wide parallelism of a GPU. Think of the inverted index as flipping through filing cabinet drawers one at a time, while the Bloom index is more like shining a laser through a stack of transparencies and seeing which ones line up. For the ANN search itself, they build a fused Int8 kernel using the inverted file, or IVF, clustering approach. You cluster all item embeddings into thousands of groups, and at query time, you pick the nearest clusters, then score items only inside those clusters. The fusion trick is that they stream item embeddings directly from the embedding table into the dot product computation without materializing a large intermediate tensor. and they quantize embeddings to 8-bit integers, which halves memory use and lets a single instruction do the multiply accumulate. This lets them support top K values in the tens of thousands, far beyond what Faiss GPU offers. Now, the really nice consequence of having both indexes as tensors in the same model is that you can co-design them. The standard pipeline would run the Bloom filter over all 80 million items, then run ANN search on whatever survives. But ANN probing only ever scores items inside a handful of selected clusters. So all the filtering work done on items in non-probed clusters is wasted. SilverTorch flips the order. First identify which clusters to probe, then only run the Bloom filter on items inside those clusters. Since these two predicates are independent and combined with AND, the order doesn't change the result, but the compute and scratch memory savings are dramatic. For an 81 million item index with 256 probes, they only process 2.3 million items instead of all of them, a 30-fold reduction. The freed-up GPU headroom funds two model improvements that would have been latency prohibitive in the old architecture. The OverArch is a scoring layer, often implemented as a mixture of logits, that re-ranks the candidates with a richer similarity function than a plain dot product. The value model is an aggregation layer that takes per-task predictions like probability of like, share, comment, and combines them via a user-defined formula into a single composite score that captures business value. Multitask retrieval used to require replicating the entire index per task on CPU, which scales costs linearly. On the GPU, you batch all the task queries through a single index copy. The results are striking. On an 80 million item dataset, SilverTorch hits 12 and 10 queries per second versus 51 for the CPU baseline, a 23.7x throughput improvement, while keeping P99 latency around 15 milliseconds even under load. On total cost of ownership, even with the heavier OverArch scoring added, they come out 13.35x more cost-efficient than the CPU stack, while improving recall by up to 5.6% on key engagement tasks and 28% at smaller recall cutoffs. The Bloom index alone is 291 to 523 times faster than the inverted index baseline, and the co-designed ANN Plus filter is roughly twice as fast as running them separately while using a fraction of the scratch memory. There are real limitations worth flagging. GPU memory becomes the binding constraint and dictates how many GPUs you need based on index size, embedding precision, and OverArch weights. The paper notes hitting out-of-memory errors when Bloom filter size grows too large. Int8 quantization caps out at around 0.92 recall and can't reach 0.95, which the authors handwave by saying the OverArch makes up the difference. But that's a real trade-off in domains where pure ANN precision matters. The Bloom filter introduces false positives, which they rely on the downstream ranking stage to clean up, an assumption that breaks if ranking is also approximate. Real-time freshness, where new items need to enter the index continuously, is acknowledged as future work and is genuinely hard in this architecture, because the indexes are baked into model snapshots that take an hour to build. Now, let's walk through some questions you might have after hearing all of this. First, why is the Bloom index actually faster than an inverted index, given that inverted indexes are widely considered the gold standard for filtering? The key insight is workload mismatch. Inverted indexes shine when features are sparse and selective, like text terms, where most documents contain very few of any given word. Recommendation features are dense and broad, so the posting lists are long and the merge step dominates. On top of that, inverted indexes require sequential list walking and irregular memory access, which destroys GPU throughput. The Bloom index trades exactness for compact, bit parallel operations that map perfectly onto how GPUs execute, and the rare false positives get filtered downstream anyway. Second, why does reordering the ANN and filtering steps not change the result? Because the two conditions are joined with a logical AND, the final answer is just the intersection of items that pass both. Intersections are commutative, so it doesn't matter which set you compute first. The savings come from the fact that ANN probing implicitly restricts you to a small subset of clusters. So by computing that restriction first, you avoid doing filter work on items that were going to be discarded by the ANN step regardless. Third, why does putting everything in one model actually improve recall, not just throughput? It's not the unification itself that improves recall, but what the unification enables. Once ANN, filtering, and scoring all live in one GPU runtime, you can afford to retrieve tens of thousands of candidates instead of 1,000, run a richer learned similarity function on top, and combine multiple task heads, all within the same latency budget. In the old stack, network hops and CPU bottlenecks meant you spent your latency budget on plumbing rather than modeling. SilverTorch redirects those saved milliseconds into more sophisticated computation. For large-scale recommendation systems serving hundreds of millions of users, the most actionable lessons here are about co-design and unification. If your retrieval stack is a constellation of CPU services for ANN, filtering, and feature lookup, you're almost certainly paying a heavy tax in cross-service orchestration, version skew, and lost co-design opportunities. The Bloom index pattern in particular is worth examining for any production filter layer with moderate cardinality features, since it converts what is usually a CPU-bound sequential workload into something a GPU can chew through in parallel. The probe then filter ordering is essentially free if you control both stages, and the trick of caching pre-computed item embeddings on the GPU to enable richer learned similarities is the kind of move that lets you blur the line between retrieval and ranking, addressing the long-standing consistency problem where the retrieval stage and the ranking stage optimize different objectives. More broadly, this paper is a strong argument that the multi-stage recommendation pipeline, while conceptually clean, has been calcifying around organizational and historical boundaries rather than computational ones. As GPU memory grows and Int8 inference matures, the case for collapsing retrieval and the early stages of ranking into a single model gets stronger. For production teams, the practical path is probably incremental. Move the ANN index onto the GPU first, then absorb filtering, then start experimenting with learned similarity layers that would have been infeasible to serve before. The throughput headroom you unlock pays for the model complexity you want to add.